So today we're going to talk about cross product. And what did we talk about last time? Dot product, right? Okay. Now the symbol for cross product, guess how does it look like? It's a cross, right? It's a cross product. It's a cross. It's a cross. Looks like multiplication, but it's not multiplication. It is the operation between two vectors. So let me make it. So it's a cross item, like this. Okay. It's a cross product. So this one here has to be a vector, and the other one has to be a vector. Multiplication is only for number, okay? But here is operation between two vectors. And last time the dot product is also operation between two vectors, but this is another product. It's called a cross product. Before we go on, we actually first want to reveal determinant or maybe introduce you to determinant, okay? So what do you mean determinant? So when you have a matrix, say this is a matrix, it's a matrix, it's a 2 by 2 matrix, right? Okay, how do you find the determinant? The determinant of this is going to be AD minus BC. So cross, multiply, and subtract. So A times D minus B times C. Okay, let's for example, this one. What will be the determinant of this 2 by 2 matrix? Yeah, so 2 times 4, subtracting. Yes, 1 times -6. So that will be equal to 14, right? So that's the determinant of the 2 by 2 matrix. Now, what about determinant of 3 by 3 matrix? How do you do it? Yeah.
It's like the laser.
Like a laser?
Yeah, because like A is like, it goes that way, so you have the leftover, and then
Oh.
those mobile games where you like
Yeah.
and there's 3 of the same.
Yeah, you eliminate, right? Eliminate that. So it's like this, okay? So you will take, okay, I'm going to use a pointer, okay? So you're going to take this, oh, battery low. It's not good. Okay, there might be some trouble, but let's continue and work on this. So we will have, we take this A, okay, you can expand along the first row, okay? So along this first row over here. Now, you will take the first one. All right, so take the first one, and then you're going to use the first one, right? And then you eliminate the column and row that contain that one. So after that, what do you get? You get this submatrix, right? And then you're going to put it over here, submatrix. And then, you see it? Okay. And then after that, you're going to repeat with the second one. You're going to take this, and you're going to have this one over here, right? But however, do you notice that there's a minus sign over here? The minus sign over here? Mm-hmm. It's because when you expand that, the sign is going to be this. It alternates the sign. Positive plus minus plus. The sign is going to be like this. So the first one will be A1 and times this, the determinant of the submatrix. And then now it will be minus A2. And then you're going to eliminate this one and this one. Then the submatrix will have this and this, right? It will be this one right here.
Okay. It's the determinant of the submatrix.
Yeah, that's a determinant of the submatrix. Yeah. So A1, and then you cause that one, and then A2, you cause the row and column of that one. And then finally, and then you will take A3. This time, remember, this is addition, subtraction, addition, right? And then you take A3 here, and then you cause out the column and row that contain A3, and then you end up with this submatrix, right? And then the determinant of this submatrix over here. Okay, so I think the tricky part here, sometimes you forget this is actually minus. Okay, so plus, minus, plus. Okay, question? So that's how you get the determinant of a 3 by 3 matrix.
So
Yeah.
that's it.
Is this what? Okay, this is going to help us. Okay. So for example, let's try this example. Okay, what will be the determinant of this 3 by 3 matrix? So we take what? We take 1, right? And then times the determinant of what? What's the matrix? Yeah. 0, 1, 4, 2, right? Okay. And then the second one, remember the second one here is a minus sign, right?
3, 1, 5, and 2.
Yeah, so it's minus 1. Minus what? Minus 2. No, minus 2. 2.
2.
Yeah, the 2. Okay, this 2 here, right? The 2 over here.
Yeah.
And then
3, 1, negative 5, and 2.
you got it. 3, 1, negative 5, 2, right? And the last one will be what? Plus negative 1 times the determinant of 3, 0, negative 5, and 4, right? Okay. Yeah. You have questions?
Okay. If the negative sign there switched to a plus, how would we rearrange the matrix in like the matrix that is like 3, 1, minus 5, 2?
3, 1, negative 5, 2. Oh, I'm
Just plus instead of like.
Oh, okay. Here you see the next step here. So what did you do? So over here, you have negative 2 here. And then you remember 2 by 2 matrix, the determinant. 3 times 2 makes 6. And then you subtract 1 times negative 5. So when you subtract negative 5, become adding 5. You see it?
You meant if we were not so if we were manipulate the symbol here, so instead of a minus the second one, we add the second one, what would the A-side matrix look like?
Oh, if you put a minus sign here, why do you want to make it inside? So then you can then you will put the negative sign in each. I think you put the negative sign in each number in here, here, and here. So you want to distribute the minus sign here. You can actually distribute into each number because that way you will get the opposite of this. Oh, actually, not the number. Oh, you distribute the minus sign in one of the either the column or the row. So you can put negative 3 and plus 5. Okay. Yeah, if we want to distribute the minus sign into this matrix and to get the same determinant, okay? So you just said that if you want to do that, so then let's try this. Oh, my Apple Pencil went out of this. I'm going to stop the recording right now. I'll go back. Okay. All right, so all right, so now once you know the determinant of the determinant of a 3 by 3 matrix, that's going to help us to find the cost part, a way to provide us a way to remember how to find the cost product. Okay, so a cost product, according to the definition, is actually a vector that is orthogonal to both vector A and vector B. So A cos B should be a vector that is orthogonal to both A and B, and it's going to go according to the right-hand rule. So if you put your the forefinger here in the direction of A and then curl to the direction of B, then your thumb is going to point to the direction of the cross product C. Okay, now how do we do that? Now you guys just talk about that. You guys remember, right? And then when two vectors are orthogonal, the dot product equals 0. So A dot C will be this. A dot C will be 0. So that will give you this equation. And then B dot C will be also equal to 0. So that will give you this equation. Now you have two equations, and you need to solve for C1, C2, C3, because we're looking for the vector C. Then I did all the algebra and solve these two equations, solve for C1, C2, C3. And I come up with this. C1 is this, C2 is this, C3 is this. Well, that will be this way. It looks very complicated to remember, but now the determinant of a 3 by 3 matrix is going to help you to remember this. Okay, to remember this, you put I, J, K, the 3 standard bases here, I, J, K, and then the second row you put the vector A, and then the third row you put the component of the vector B. So component A, second row, component B, third row. First row put IJK. Now let's expand this, okay? Let's expand this and see what we get. Let's find the determinant of this, right? So what do we get? So you will have what? What do you have? In the I here, right? So what will be, then you cause the column and that, so you get what? A2, A3, B2, B3, right? And then after that, you have to remember minus, right? Yeah, very good. So it is addition, subtraction, addition. So here, remember, it's a minus. Minus.
Something went wrong. Please try again.
My Siri. Okay. Okay, I'm sorry. So minus, and then this will be the J, right? J. Okay. And what will be the determinant of the submatrix? Yeah, you cross out the column and row containing the J here. So A1, A3, and then B1, B3, right? Okay, let me see how enough space. And then finally, what do you have? Adding, right? The vector K. Yeah, you got it. And then what do I put over here? A1, A2, B1, B2, right? Okay, let's compare this one with this one, okay? So the I component, remember this is actually in the I component, right? In the I component over here. Okay, so in the I component here, is it A2, what's the determinant of this? A2, B3, subtracting what? A3, B2, isn't this one? Okay, and then look at this one. Okay, what would be this one? What's the determinant of this? A1, B3, right? Minus A3, B1. But then if you build a minus sign in this, right? You should build a minus sign here and here. Okay. What does it become? A3, B1, A3, B1 here, right? Subtracting what? A1, B3. Isn't this one? Right? And then similarly for this one. This is going to match with this, right? So remember the cross product is actually better to remember that as a symbolic determinant of this 3 by 3 matrix. What will be the first row? IJK. What will be the second row? Component of A will be the third row. Component of B. Then this will be the cross product. Okay. The symbolic determinant of this is the cross product. Okay. Right. So here I actually write it out in another way, right? So you see it in the note. Okay. Right. Again, I put it down here. IJK, component of A, component of B. Okay, let's practice on this. Okay. I'm giving these two vectors, A and B. Okay. Let's find the cross product of these two. Remember, we're talking about cross product, right? Okay, what should I put for the first row? IJK, IJK, okay. And then second row, 1, 3, 4. And the last one, 2, 7, -5. And then, okay, let's expand this, okay? Now, when you expand, remember the sign here has to be plus, minus, plus, okay? So and then here is a minus. Remember that's a minus. Okay. What should we put over here? The I. 3, 4, 7, negative 5. Yes, you got it. Okay, for this and this one, minus, expand this. 1, 4, 2, negative 5. 1, 4, 2, negative 5. Okay, and the last one here, 1, 3, 2, 7. Yeah, 1, 3, 2, 7. Okay, and then now you can just get the determinant of this, and you do 3 times negative 5 is negative 15. Subtract 4 times 7, so you're subtracting 28. Okay, and then finally this will be the vector. Okay, so you can put it in the IJK form, or you can put it in the angle bracket form. If I put it in the angle bracket form for vector, what will be the first component? Negative 43. The second one, 13, and the last one, 1. Yeah. So both represent the same vector. Okay. Yeah.
Can you cross product like multiple vectors, more than 2, or
Only 2. Only vector. Only 2 vector. One vector causes another vector. Yeah. Well, later on you can cause again, but you will first get the result of the cos product, the 2 vector, then you can cause again. Okay, so Wing's question here is, if you do A cos B, right? Then you can cause another vector again. You can also cause another vector again. Okay, so you first need to get the cos product is between 2 vectors. Okay, then you get the result here, and you can cause another one.
But when cross product is 2 vectors, it's creating an extra dimension, right? When you do the right hand rule. So
it's actually again, what's the result? What's the result of a cos product? It's again a vector. It's again a vector. Okay, so cos product has to be vector cos another vector. Yeah. All right. So maybe I shouldn't put a C here because I already used a C for the result of that. Okay, maybe that will be a D here.
Can you do a cross product on a 2-dimensional vector?
Do you think? What do you think? Can you do a cross product 2-dimensional vector?
Yeah.
We won't call that 2-dimensional because you need to have a 3x3 matrix. What happens? You have a 2-dimensional vector, so you can put IJK, right? And then you just put A1, A2, but then the last one you put 0. And then B1, B2, and then the last component will be 0. Then you can do cross product this way.
Can the cross product be expanded to like using the nth dimensional vector? To like an nth dimensional space, can it always
Cross product here you only for 2. 3 component has. So it's 3 dimension.
Is it because of the relationship of orthogonal to 3-dimensional space?
Yeah, right. Are you trying to confuse me? but that's good thinking. Okay. All right. Only for 3 by. Okay. Good question. So it has to be a 3-dimensional. The vector here has 3 components because you have to have this matrix here. Okay.
So you can't cross a 4-dimensional vector.
I don't think so. Maybe you can.
I think you can, because like if in 2 dimensions you have 1 right angle, in 3 dimensions you have 2 right angles.
But how would you define that? That would be very interesting.
Just be like a 4x4 determinant.
Yeah, but what will be the procedure? What's the
Okay. How about you research on that and put it in the discussion? Okay. But right now, cos product here is going to be a cos product of a vector with vector, and both vector here has to be 3 dimension. Okay. It has 3 components. Yeah. Okay. So you construct the cos product this way, right? So will be perpendicular, or another way we say orthogonal to both A and B, right? So you have A here, and then you have B here. There's 2 vectors. Then C is going to be the cos product. There's 2. it's going to orthogonal to both A and B. So the theorem here say the vector A cos B is, what do you think I should put it here? Orthogonal. Okay, orthogonal. Or say perpendicular. But I think it's better to say orthogonal. Okay, spell this orthogonal. Every spell that to me. O-R-T-H-O-G-O-N-A-L. Okay, orthogonal. Yeah, when you have more than 2 dimensions, then you say orthogonal. Perpendicular usually only used on 2D. Okay. Okay, and so what would be the direction of the cross product according to what kind of rule? The right hand rule. Yeah, see here the right hand rule. Okay. All right. Just like the other one. Last time we talked about. Do you guys remember last time the dot product? Okay. So if you have the dot product, okay, put a big dot here, and the big dot of say A cos B. Do you guys remember there was a theorem we talked about last time? It was the magnitude of, you got it, magnitude A times magnitude B times what? Cosine of theta. And what is the theta? The angle between them, right? So you have A, okay, and then you have B. Okay, okay, maybe this way. Angle, vector A, vector B, and then the angle between them here is theta. Then the dot product of that is equal to this, right? Today we have a similar theme for cos product. Okay, we're going to talk about cos product. Yeah, there's a cos product over here. That's equal to the magnitude of A times the magnitude of B, and then times sine of theta. Okay, you see the similarity? That product here times cosine theta. This one times sine theta. Okay, this is the magnitude. Okay, what about the direction? Direction is according to what kind of rule? The right hand rule. Okay, right hand rule gives you the direction, and this will give you the magnitude. Okay, now vector is completely determined by magnitude and direction, right? So we just talk about how do you get the magnitude of the cross product and of A and B? Is what? Everyone say that? What's the magnitude? Magnitude of that is what? Magnitude of A times what? Magnitude B times what? Sine of theta. Yeah, that's the magnitude, right? Okay. That's the magnitude. And what about the direction? Yeah, direction is given by the right hand rule. Okay. So you know both. Okay, then you can determine the cross product. Okay. So in this direction and with this magnitude. Okay. It is perpendicular to both A and B, and the orientation determined by the right hand rule. And the length is this, right? The length is this. It's given right here. This is the length. Okay. All right. So now we have a corollary. That means it got it from a theme. Okay, something got it from a theme. Okay. Kind of like the side product. Okay. So two non-zero vector A and B are parallel if and only if the cross product is equal to the zero vector. Okay, it's equal to the zero vector. Can you think about why? What happens when they're parallel? What will be the angle theta between them? Zero or pi, right? What's sine of zero? What's sine of pi? Yeah. So when they're parallel, then this part here, the sine of the angle will be zero. The whole thing will be what? Zero. So we have the magnitude of zero. Okay. So you have a magnitude of zero, and that is a zero vector. Okay. See here, the result of a cross product here is actually a vector. Okay. It's a zero vector. It's a zero vector. Okay. Vice versa, if they're non-zero vector, what happens when the cross product equal to zero? Well, these two, the magnitude are not zero. The only way to make zero is sine theta equal to zero. So theta has to be either zero or pi. So they are parallel. Okay. So this is a if and only if statement. Okay. Okay. Now maybe repeat after me. Okay. Just like last time. Okay. I say once and then you say once, right? Two non-zero vectors A and B
Two
non-zero vectors A and B
are parallel
are parallel.
if and only if their cross product is a zero vector. Very good, very good. Okay, good job, good job. Okay. Okay, compare with, okay, now I put it over here. I actually compared them, okay? The two vectors are orthogonal if and only if what? From last time.
If the dot products are equal to zero.
You got it, good job, okay? If and only if the dot product is equal to zero, right? If they're orthogonal, you just talk about it, okay? Okay, if and only if A dot B is equal to zero. You guys catch up very fast. Okay, good job. Okay, that's equal to is it zero? Is a scalar or vector? Yeah, it's a scalar. Okay, scalar. The result of that product is a scalar. Okay. Today we talk about these two vectors are parallel if and only if what? Yeah, the cross product A cross B is equal to the zero vector. Okay, you see? Okay. Okay, without looking at it, I will say that product equals zero. Two vector will be what? Orthogonal. Cross product equals zero. Parallel. Okay. All right, good job. Okay, all you think about this. Okay. Okay, cross product. Okay. We have a geometric interpretation of the theme that we talk about, theme 9. I put it down here. This is theme 9 over here, right? It says the magnitude of the cross product. Remember, this means it's the cross product, right? It's magnitude A times magnitude B times sine theta. Now, looking at this, okay, magnitude of A, it is, well, what's magnitude of A? Is how long is this, right? How long is this? This is this one here, that is the magnitude of A, right? Okay. Now let's think about what is this one here? So B times magnitude B times sine theta. Okay. Well, this is magnitude is this part right here, right? Is how long is this? Do you think it's the magnitude this? Do you agree? Right? So the magnitude B times sine theta give you the magnitude of this, right? So you have this times this, right? Does it look like this one? Magnitude A times this, magnitude A times this. So it's like base times height. And what does it give it to you? The area of what?
Box.
Yeah, the area of the parallelogram, right? Isn't that the area, right? So yeah, the area over here is actually the same as this, right? That's the area of that. So if you have A cos B, the magnitude of that actually is the area of the parallelogram that has A and B as the side. Okay. So next time, if you try to find the area of a parallelogram, you can find this vector and this vector, and you do the cross product of them. Question? No? Okay. All right. Yeah, so the area is this. So it says the length of the cross product of A cross B equal to the area of the parallelogram. Okay, it's this area over here.
I thought it was A and B's area. The LL. Not including that D sine theta.
You need the sine data here. The B, the magnitude B is this one. How long is this? But the height of this is this one. It's the magnitude B times sine of theta. Okay. This is the height of the parallelogram. We need the sine data.
That is the projection of B on the.
No, projection is going to be down here. The projection B onto A will be here.
I need to put aside. I thought the area of the parallelogram is the same as square. A plus B.
Okay, go back to geometry. Okay, so if you have something like this, okay, so parallelogram, okay, say this is A and this is B, okay, it's not A times B, okay. What do you do over here? You can actually cut this and put this part over here, Then you get a square, right? Do you agree this one here is a square? It's actually A. It's going to be this A, and then times this, which is this. It's not B. This one here is what? It's going to be B times what? B times sine of this angle. Sine of whatever this angle here, say theta. Sine of theta.
Like you cut off that little triangle there, and you know there compensates for that lost area. And this is where the A and B points go.
Yeah, so this will be a y triangle. This one here is a y triangle. This is not y triangle. This is a rectangle, right? Do you agree? This one here is the same as this one. Okay. You see?
This is where you can still use the A times B because then you can cut off that triangle.
No, you cannot use it because that length is not, it's not A times B. That's it. I mean, you can think of it like the shadow. I mean, like we're just doing direction and beam on A. So it's like, it's not the same thing. So you can't create a parallelogram.
Okay, let me make a.
Think about it, like if you were to shoot it in place.
Okay, let's just do it. Okay, here. Okay, so say this is 3. Say this is, say, 2. Would this area here to be 3 times 2? It's not. Why? Well, if you do it this way, cut this part and put it over here, you're going to get a rectangle over here, right? And what's the area here will be what? 3 times the height of this rectangle. The height of this rectangle is a 2? No, it is what? It's this. And what would that be? Say this angle over here, say it is 30 degree. Let's say 30 degree. Then what will be this one here? This one here will be 2 times sine of 30 degree, right? So that is going to be, yeah, so that will be that one, okay? So you need the sine of theta there, yeah. Okay, now let's look at this example. Can we find the area of the triangle with these 3 vertices? Yes, we can, of course, right? Well, this is in 3D, right? You can try to put the dot there, but we don't need to draw the picture, but we can do it, okay? So maybe we just put 3 dots over here. P, okay, and then Q, and then R, okay, like this. And what are we looking for? We're looking for the area of this triangle in space, okay, in space. Now, how do we find the area of the triangle in space? Think about it. Well, we can actually make, let's think about it. Can we make a parallelogram? Right? We can make a parallelogram. We can find the area of this parallelogram by using what? The magnitude of the cross product. Okay. How is the area of the parallelogram relate to this triangle? Area of the triangle.
It's double.
Yeah, it's double. So we can find the area of the parallelogram and then divide by 2 to get the area of a triangle, right? Okay. All right, so let's find the area of the parallelogram first. So we know that it's related to the cross product. Okay. So what's the cross product here? It's cross product of this with what? Cross product of PQ with PR. Okay, so with this. So that's the cross product of PQ with PR. Okay. So we actually calculating this. We know. Do you guys know how to find cross product, right? Okay. But let's find PQ first. Okay. Okay. Actually, I put the here. Okay. Let's find PQ. So what's PQ? Yeah. So PQ here, because P is this vector, right? This one, the P here is 1, 4, 6. And then Q is what? Q is -2, 5, and -1, right? So to find the vector PQ, you take the component. Okay, right here I'm using rhythm preferred way. So you stack them, you subtract them, right? So you take the component Q, subtract that, right? So the first one will be -2 minus 1, right? And the second one will be what? 5 minus 4, and the last one will be what? -1 minus 6. Okay, and what do we get? Yeah, you get -3, 1, and -7, right? And similarly, you can find PR, right? So R here is going to be 1, -1, 1. So what is PR? Yeah. So you're going to take the component R, subtract the component of P. So 1 minus 1 will be what? So -1 minus 4, -5, and then 1 subtracting 6, -5. So you get this, right? Okay, now you put you find the cross product, okay, because the magnitude cross product is the area of the parallelogram. Okay, so right here we're doing cross product. Okay, remember how do you do cross product? You put what? IJK. And what should I put for the second row? P. Okay, let's put P there. PQ. Okay, PQ is what? -3, 1, -7, and then PR. 0, -5, -5. Okay, and then you just compute the determinant of this, right? And then I think I got the result here, and then it turned out to be okay, and turned out to be -40, and then here is -15, and the last one here is 15. Okay, you just do that.
In the PR, the Y component.
Why is it 0, -5, -5?
Yeah.
PR. Okay, P. Okay, let's put the P here. Okay, P is 1, 4, 6. Okay, so from this two, you can calculate the vector PR. You just take the component and subtract. So you would take 1,
Then you
subtracting 1, you get, what's the first component? 1 subtract 1 will be 0. Negative 1 subtract 4 is -5. 1 subtract 6 is -5. So that is PR.
oh okay oh okay. I think-
Yeah.
Oh,
So this one here is, this is for the vector PR.
okay.
Okay. And then this one here is for the vector PQ. Right here.
Oh, we're computing them from the points. We're given points, right?
Yeah, we're given the 2 points.
Uh,
Remember when you know the starting point and the ending point of the vector?
oh,
You use the component of the ending point, subtract the
Yeah.
component of the starting point.
I thought we were given the vectors.
Yeah, those are the points. Okay.
That makes
Yeah, that makes sense. Okay. So those are the points. Those are the points. Those are the points. And then here, this is a vector. So to compute the vector PR, you would take the ending component, the component of the ending point, subtract the component of the starting point to get the vector.
You got I-40 minus J-15 plus K-15. That's the vector.
Yeah, the cos product is -40, -15, and 15. Yeah.
So you distributed the negative change to the negative.
Over here, I skipped the details. You guys know how to find the determinant, right? It turned out to be this. Okay. All right. So now we find the cos product. How do you find the area of the parallelogram? This one here. That's the magnitude of the cos product, right? So what's the magnitude of this? You square? Yeah. You square each component and then what? You sum them up, right? So now you take each component square and then you sum them up. They turn out to be this.
Who's supposed to put that in there?
Yes, yeah. I was going to ask you, okay? This is the area of what? The parallelogram, right? But what are we looking for? Area of a triangle. So we should cut this in what? Cut it in half, right? So this should be half of it. Half of this. Okay, so what's the area here? 5/2 times square root of 82, right? You got it.
Square root of 2050.
And maybe, yeah. Maybe they turn out to be equivalent. Yeah, you can double check. All right, now we're going to have I'm going to put the two themes together, okay? Just try to refresh your memory, okay? The cross product is orthogonal to both A and B, and the magnitude of that is equal to magnitude A times magnitude B times sine of theta, right? So this is theme 8 and theme 9, okay? Now we're going to apply this to the standard basic vector ijk, right? What are the angle between I and j? What will be the theta? Theta is what? pi/2, okay? Now let's try I cos j. What's I cos j? What do you get?
K.
K, yeah, you got it. That's equal to K. Or why? Right? Here is I, right? And then you curve to, here's I, and then you curve to j. Here, that will be K. It will go this way. And the magnitude should be 1. Because sine of pi/2 is 1, right? And the magnitude A and magnitude B both are 1. So 1 times 1 times 1. So the magnitude of this I and J should have magnitude to be 1, and in the K direction. So it's 1. Okay. All right. So all of this has actually magnitude to be 1. Okay. Let's try the other one. what will be J cos I then? It's a switch it. Negative K, yes, you got it. It should be the other way. Negative. Okay. So J and then cos to I, right? The cos I, and then here it goes down to negative K, right? Okay, good.
I think it's negative because of its alphabetic. Is it because of the alphabetical order?
Okay, so it's not commutative. In fact, it here turned out to be opposite. Okay, so maybe easy way to you switch the order. Okay, you do I cos J, and then you just put a minus sign in front. Okay, you switch them, commute them, and you put a minus sign in front. Okay, what about J cos K? J cos K? J cos K? I? Wow, you guys are good. Wow, I'm impressed. Okay, oh, way to go. Okay, I K cos J.
J.
Yeah, forgot. Remember, you get to switch them. You can switch them is J cos K, but then you put a minus sign in front, right? So it is what? Negative I. Yes, you got it.
Oh, I was talking about the X.
Oh, the next one. Okay. K cos I. K here. Cos I. That is J. Wow, you guys good at it. See, you guys are smart. Okay, and now what about I cos K? Negative J, right? Negative J. Okay, good. Okay. I know some people had trouble with the right hand rule, and then how should I call? Try it, okay? Try it. I think this class and also physics class is the one the student always use the right hand and do Excel. In physics, right? The physics for the magnetic, yeah. Okay, yeah.
Okay, so this.
Huh? K.
I cross.
I cos K. Okay, I. And then K, this is I, right? K is going up, right?
Yeah.
So you go up.
Yeah.
Then this will be,
Negative. Or negative J.
yeah. So I cos K, so it's negative J.
Yeah.
Negative J. If I make it difficult, you can switch them and then you put a minus sign in front. Huh? Okay, so you see that, is it commutative? Okay, so this is the right hand rule, okay? So think about the I and then K and J, play with it, okay? Use your right hand. It's a good exercise, okay? So you see that is the cos product is it commutative? Yes. If commutative, then I cos J and J cos I will be the same, right? Yeah. See, I cos J is what? I cos J is K. And what's J cos I? Negative K, right? So they're not equal. So is it commutative? Yeah, so it's not
It's
commutative.
sort of a negative.
Yeah, actually, it's opposite. Okay. Yes.
But do you consider it like multiplication? Like when we say products, we're saying it's multiplication, right?
Multiplication is only for number, but we are talking about vector. So we cannot say multiplication.
So we can't.
Yeah. Why not we're doing vector? Vector cause another vector. When you talk about multiplication, we talk about number, two real number. Yeah, multiplication is just 2 times 3. Okay, here has to be vector. What about this? Okay, is it associative? Well,
Yes.
yes. Okay,
No.
try this one, maybe. And then you say whatever you say. Okay, here I cos J, and you put a parenthesis here, or you put a parenthesis here, right? These two look similar, right? But this one you put a parenthesis here. This one you put a parenthesis here. So you associate these two first, or associate these two first. The result turn out to be the same. Oh no, not the same. The result turn out to be what? Different, right? A different result. Okay. So that means it is not associative. Yeah. Okay. So the associative law for this does not usually hold. Okay. Does not usually hold. Does not usually hold. Okay. So in general, it's not associative. So you say, oh, beside this, what else then? Beside this, actually everything else will be normal, kind of normal. Okay. So beside this, other property will be very similar. So you see, A cos B is what? Opposite. Yeah, opposite of B cos A. Okay. You just need to put the opposite sign there. Okay. So if you ever have trouble doing the right hand, you can switch the order and then put the minus sign in front. Okay. All right. And then also the scalar multiple times the vector and then cos that, you can take the scalar in front. Or you can put the scalar with the second vector. Okay, here, kind of like the distributive property. Okay, and here you can actually kind of like a distributive property. This one here, A dot B cos C is A cos B dot C. Okay, so over here you have a dot product, right? And then here I have a cross product. Then it's the same as A cos B started with C. Well, this is something if you're looking at this, later on I'm going to talk about that. It's called this kind of form. So you have dot and then cos and or cos and then dot. I'm going to talk more about this type of product. Okay, and then here A cos B cos C is this. Kind of interesting, right? This one here. Now the proof of this, I'm not going to actually for number 5 over here. Here is a proof for number 5. Okay, number 5 for this property. This is the proof. Okay, but the rest here I didn't prove it. But if you want to look up the proof, it should be in. You can actually try to prove it yourself, and it is true. Okay, trust me. Okay, now I'm going to talk about triple product. Okay, before we talk about triple product, do you guys want to take a break? Okay, let's take a triple break. Okay, let's take a 10-minute break. Okay. Right? You guys want to leave a little bit early? You get it done. Okay. Okay, triple product. Triple product. The first one we talk about is this. A dot parenthesis B cos C. Okay. This one here is called scalar triple product. Okay. It's called the scalar triple product. So that means the result here should be a scalar, right? Why is it scalar? Let's think about it. What is B cos C? What's the result? Result is here is a vector, right? It's a vector. The cross product of two vectors is a vector, right? And then dot product. After that, okay, and then you do the dot product, right? What happens when you have a vector dotted with another vector? What's the result? The result here is scalar, right? Scalar, LAR, okay? Remember that product, you multiply the component and add them up, right? So result here is a scalar. So that's why here, this one here is called scalar triple product. Scalar triple product. Okay, that's called scalar triple product. Okay. The result is a scalar. Okay. And an easy way to remember this is actually you put the vector put a component for the vector A on the first row, A1, A2, A3, another component for vector B, B1, B2, B3, component for vector C, C1, C2, C3 here. Then the determinant of this will be the result for this scalar triple product. Okay. How do you yeah, so you can actually try it. Okay, we can prove this. Okay, so you got this. So the scalar triple product of A dot parenthesis B cross C is equal to this. Now do not do this. Okay, so if you put something like this, something's wrong. Hold on, I'm going to charge my. All right, so we just talk about this. This is called a scalar triple product. Okay, do not do. And I was asking you guys, what's wrong if I had this expression? Well, because if you do that, you would do this two first. Then that will be a scalar. But then scalar cannot do a cross product with another vector. Okay, so this one here is wrong. And the only way that you can fix it is you put a parenthesis here. Okay, so you need the parenthesis here. Okay, then it's not wrong. Okay, so you do need the parenthesis here. Okay, now we're going to talk about this. Okay, looking at this, this is something we call the parallelepiped. Is that how you say it? Parallelepiped. Parallelepiped. Okay. this it's called parallelepiped.
I've never.
You think so?
Parallelepiped.
You agree? Parallelepiped.
You got it.
You got it.
Sorry.
Okay. Yeah. So the base here is a parallelogram, but then each face here will also be parallelogram. Okay.
All the way.
Every face, each face of this solid will be parallelogram.
C at the bottom to A and B, or is it?
C is not. Okay.
Okay.
So what do we have here? So we have actually this is A. Okay, and this is B, and C is actually like going inside a piece of this paper, this page, C.
But
Okay,
it's
go
not
inside.
at a right angle to
Not right angle.
Mm.
It's not a right angle.
I'm sorry, what's just effective?
Have it?
Is it planes or?
I think the formal definition, you can have a formal definition. However, if you look at here, see, each face here will be a parallelogram. Okay, so you can think about it's a parallelogram, and then you can like shift it, and pile them up and get a parallelogram of it. Okay, rectangular box is a special parallelogram, right? So if we have a rectangular box, that's also a parallelogram. It's just a special one, right? Yeah. So this one here is parallelepiped, but it's not a right angle. Okay, it's not orthogonal to the base. Okay,
It's not like an extrusion. It's going up.
Yeah. So you can try to think about the parallelogram, and then you go this
Okay.
way, parallelogram go that way.
Cube, isn't it?
Huh?
It's like a slanted cube.
Well, slanted cube. Yeah, that you can think that way. But the official word is parallelepiped. Okay. So each face will be parallelogram like this. Okay.
Is a cube by itself a parallelepiped?
I just said that.
Yep.
Okay.
Take that.
Cube is also a parallelepiped, right? Yeah. It's a special case. Rectangular. Okay. Now let's think about what will be the base. What will be the area of the base? The area of the base, which is I'm talking about this,
That's the same
the
thing.
base.
Sine of whatever.
The base over here, right? Do you guys remember how do you find the area of a parallelogram, right? So what's the area of this parallelogram? take the cross product of these two and take the magnitude of it, right? Okay. I like that one. Okay. And then, okay, you know the base, right? If you know the base, how do you find the value for this solid? It will be base times what? High. That base times high, right? Yeah. So the high over here will be actually from here to here. Do you agree? From here to here. That is a high, right? Okay. So this base times this high. Okay, look at this high here. How is it related to the A? Is it magnitude of A times what? This angle is theta, cosine theta, right? So magnitude of A times cosine theta. So basically, the value for this will be, yeah, remember this one here is the H, right? That one was the H. That over here is the H, right? So is the base area. So this is the base area. The magnitude of B cos C. Okay, this gives you the base area. This is the base area. Okay. This is the base area. Okay. Which is this one right here. Okay. And then you times a high, that is going to give you the value for this parallelepiped. Okay. Now this one over here, according to, does it remind you of the dot product of things when you multiply by cosine theta? Does it remind you of the dot product? Right? Okay. Let me write it down. So do you guys remember how do you do dot product? Right? So let's say A dotted with C. How do you do A dotted with C? That is what? Magnitude of A times magnitude of C times what? Cosine of theta, right? Okay. This one here has a cosine theta here, right? So this one here is a dot product of this vector B cos C with this vector A. Remember that product is commutative. So you can actually put A here and a B cos C here. So this is the magnitude of A dot B cos C. Now I'm going to ask you, do you guys notice this? What do you call this?
Wait, you said it's commutative, so you could put the A where?
Here. You can put A dot B cos C or B cos C dot A, something. This.
Okay, yeah.
Yeah. Yeah.
You put,
So this one here is the same as B cos C dot A.
Right.
Something. Okay, something. Okay. All right. What do you call this? So we actually proved this. The value of the parallelepiped determined by these three vectors. Okay, what are these three vectors? Right here, A, B, C. These three vectors determine this parallelepiped, right? And to find the value of this, you just need to find the magnitude of this scalar triple product. Do you remember scalar triple product, right? We talk about this. This is called the scalar triple product. Scalar triple product. Yeah, A dot B cos B. Yeah.
It's, I mean, I guess it's, I'm not, it's just a technical, but is it absolute value or magnitude?
A magnitude. It's a magnitude. It's called a magnitude.
No,
It-
isn't the inside,
it's
wouldn't
not
the
the
inside be a scalar?
Inside is a scalar. Yeah, inside is a scalar. Well, in this case, the magnitude or you call the absolute value, you can interchange.
Okay.
You can interchange. Yeah. Now, I'm gonna ask you. If I put it this way, and if I put it this, let me ask you. If I put this value of this is equal to B dotted with A cos C, would that be the same? I mean, the magnitude of this? Does it equal to this also? The value of this? Does it equal to this?
If A cross C is giving you a different right-hand rule equation, then B cross.
It actually turn out to be the same because it just has a 3 vector here, right? It doesn't matter. It doesn't matter which one you take it as a base, right? So if you take this A cos C here, A and C here as a base, and then this will be the same. Those are the 3 edges of the parallelepiped. You can actually equal to.
How
Yeah,
come
hold
you
on.
just say it? I thought you can't do this.
Well, okay, this will be a question for you to think about. It's actually, to think about at home. Both of them represent the value for this parallelepiped. This one or this one. Because if you switch, those are the 3 edges of the parallelepiped. The order doesn't matter, right? So you can think all of them represent the value for that. So this is a sum.
This is special.
Yeah, it's a special case. Yeah. Mhm. Okay, think about it at home. Okay. Okay, now if we use that formula, okay, what formula? This one. Okay, this formula. A dot B cos C. Okay, that's called a scalar triple product. And then you take the magnitude of it, right? Hey, what happened to my red? Okay, right here. And you take the absolute value, which is the magnitude of that. Okay. And what happens if I get 0? If I get this, if this one turn out to be 0, the result, if this result here is 0, what does it mean? The parallelepiped, it has value to be 0. If it has a value to be 0, that means they're all on the same plane, right? It's the parallelepiped. So before was like this, right? A, B, C, A, B, and then C, and then you get this parallelepiped, right? This, something like that. Okay, like that. But if the value of that is equal to 0, that means it's gonna like collapse, right? The parallelepiped like smash down and become one plane, right? It's like one plane. So that means what happened to A, B, and C? Would all of them to be on the same plane? Yeah. So they must lie in the same plane. So when the value of that equals 0, okay, so it's like the parallelepiped is actually has value to be 0. So they will be at the same plane. Okay. All right. And to be at the same plane, we call that coplanar. Did I say that right? Coplanar? Yeah, coplanar means they lie in the same plane. Okay. Yeah, question.
I'm still kind of don't get why H is the.
Huh?
I still don't understand for the volume of the curve. Like, why is H equals the magnitude of A times absolute value? Like, why?
Remember, how do you find the value of a solid? You use a base area times height.
Yeah.
Right? So what's the base area? Base area is the magnitude of B cos C.
Yeah.
What is a height? Height is this H. This is A, and this is the angle theta. So A times cosine of theta gives you this height.
Well, why?
Why? Okay, sure. The magnitude of A, right? Divide by H. Oh, I'm sorry, the other way. Why? Because this is the adjacent side. It's a right triangle.
Oh.
This is A.
Okay.
This is theta. And what will be this? That will be the A times cosine of theta, right? Yeah?
Yeah.
Because this over A is cosine. So this is A times cosine, okay? A over H, I'm sorry, the other one, H over A. H over A is cosine theta. You agree, right?
Yes.
So H is equal to what? A times cosine theta, right?
Mhm.
Yeah. So H is A cosine theta. Okay. Right. Let's try this. So here it says that so if what and then what, okay? So here it says that if the volume, if what happened, if this equal to, if this base image, if this equal to what?
0.
Equal to 0. If this equal to 0, okay, then what happened? Then then A, B, C are coplanar. Okay? Then A, B, C are coplanar. So that will provide you a way to determine if they lie on the sampling or not. So you calculate the scalar triple product and see if you get the zero vector. Actually, the zero scalar, okay? See if you get the zero scalar, okay? Then if equal to 0, then they lie on the sampling. Okay, let's try the next example. I'm trying to put it here. Okay. Okay, now we have this 3 vector, right? How can I determine that coplanar? What equal to 0?
A, B, and C.
Not ABC, it's the scalar triple product. So we will calculate this scalar triple product, right? So the scalar triple product. Okay. Now how do you do the scalar triple product? You put component of A, component B, component C, like this, right? Okay, let's fill this in, okay? So what should I put at the first row? I know, but in this case, what's A1?
Oh, 1, 4.
1, 4,
Sorry.
negative 7, right? And then B,
2, 1, 1.
2, negative 1, 4, and then what else? 0, negative 9, 18, right? Yeah. So when now you have a question,
What plane is this flat on the same plane?
coplanar means they on the same plane.
So, what does that mean?
They're on the same plane.
On the same
Don't
plane?
like
There's 3 vector on the same plane. How you get 3 vector on the same plane? Okay, think about this my iPad here as a plane, right? So A will be here, and then B here, and then C will be here. So all on the same plane. A, B, and C. The 3 vectors will on the same plane, coplanar.
Can I understand it as it became like 2-dimension?
Oh yeah. So the paralleloparallel SH becomes this 2 dimension. It doesn't have the height.
Yeah.
The height equal to 0 actually.
So is it then a parallelogram like the plane?
Yeah, it's just like it become a parallelogram. But the C actually it's not parallelogram because you get 3 vector. You get 3 vector. You just like this, okay? A and then B and then there's C. You get 3 vector here on the same plane. Coplanar means you think about you, rhythm, and this all in the same class. So you are one vector, rhythm another vector, ring is another vector, all on the same class, same form. Okay.
But it doesn't become a parallelogram. It becomes some other shape.
You get 3 vector. It's not a parallelogram, right?
Like a flat parallelogram.
It's not
Okay.
parallelogram. This vectors, this 3 vector, 1, 2,
Right.
3.
I mean, it's like a parallelogram, whatever it's called, but it's flat.
Yeah.
So it's a 2-dimensional parallelogram.
Yeah. So you don't get a solid. You don't get a 3 dimension. It becomes 2 dimension. Yeah. So on the same plane, right?
I'm just trying to think of the shape.
Okay. You're trying to think of shape. Okay, let me draw it. Okay. So it was like this coplanar. So that will become. So this is the plane, right? So it's going to be A, and then you have B, and then you have C. They're all on the same plane. The 3 vector.
C is just not,
3.
it's not, there's no depth.
So that would be a parallelogram, right? It would connect the end of A.
Yes.
But then you get 3 vectors. What parallelogram? Are you talking about this parallelogram or the other parallelogram?
So
So,
it's only two-dimensional. That's really, if you look at it,
okay, so, okay, so you have C.
right, Wayne?
Say C is like this, right? Okay, maybe I try this way. So you have C go this way, right? Say C go this way, okay? Is it a parallelogram? It's a 3 vector, okay? 3 vector doesn't make a
So that
parallelogram.
has no error, right?
Vector and parallelogram are 2 different things. Parallelogram is this. Parallelogram is this, right? But then vector will be this. We just talk about the 3 vector here. They're on the same plane, okay?
Oh, so it's not
Yeah.
called an area. I thought it was connected.
They're not connected. A, B, C. This 3. Think about 3 people, okay? Those 9 on the floor, okay? It's not a parallelogram, okay? Okay, so now we go back to this. The scalar triple product, okay? So we calculate this, okay? Let's try to expand this, right? What does it equal to? That will be equal to, let's expand, remember we expand across the first row, right? So plus minus plus. Okay, so then what do we get? 1. And then what do I put here?
1.
And then negative 1, 4, negative 9, 18, right? What will be the second one? Minus, and then 4.
And then 2,
The submatrix will be what?
2, 4, 0.
2, 4, 0, 18, right? And then the last one,
And then the last one is
adding, it's minus 7, right? Minus 7. And then
2 negative 1.
2, negative 1, 0, negative 9, right? Okay. And then you calculate that, it turned out to be 0. So what does it mean, the triple, scalar triple product equals 0? That means the 3 vector will be what? Coplanar. Yeah. So that means, so the plane here, you have say A, and then B, and then maybe C over here. They're all on the same plane. Okay. So they are coplanar. Okay. Okay, another triple product will be vector triple product. Okay, what's a scalar triple product? Let's put it one more time, right? So it's A, and then what? Dotted with what? B parenthesis B cross C. Okay, that what do you call this? Scalar triple product. Product, right? Scalar triple product is this one. Okay, and the one over here is actually cos here and cos over here. You see the difference between this? They look very similar, right? They look very similar, except this one here is cos, this one is dot. This is called scalar triple product. This one here is called vector triple product. Okay, so that is called vector triple product. Okay, but don't worry about the vector triple product. Okay, I think we'll concentrate on the scalar triple product. How is scalar triple product useful? The magnitude of the scalar triple product gives you the value for what? The parallelepiped, right? And if that equal to 0, what can we say about the 3 vectors? They're coplanar, yeah. Okay. So scalar triple product will be interesting and useful. Okay, the last topic here will be, how do you say it? Torch? Torque. Okay, so what is torque? In Chinese, we call it 拧矩. Okay, so when you twist something. Okay, so over here, you have this partner, you trying to rotate, right? You're going to rotate that. Then you will have the force over here. And then this is the handle. And the force and the handle form an angle theta. And the torque is actually this vector R force with this force. Okay, it's a cross product of these two. It's a cross product of them. Okay, so it's torque. Okay, it's called in Chinese it's called 扭矩. 扭矩. Okay, like when you twist it. Okay, so like that. What does it measure? It measures the tendency of the body to rotate about the origin. So if the cross product of the F and R, that will measure the tendency of how likely this one here is going to rotate about this origin. Okay, and the direction of this torque is going to indicate the axis of rotation. Okay. Okay, let's just try this example then. According to the theme 9, remember cross product is actually related to, it's the magnitude cross product is what? Magnitude A times magnitude B times what? Sine of theta. And the one dot product is what? Times cosine theta. Okay, this one is sine theta. So the magnitude of, okay, so if you do the magnitude of the torque, yeah, so that will be, you want me to lower this? Okay.
Just a little bit, yeah.
Okay, so the magnitude of the torque is equal to the area of the parallelogram determined by these two, right? Yeah, because when you take the magnitude of the cross product, that is the magnitude of the parallelogram formed by the two vectors, right? So then this is equal to this. Okay. Okay, now let's try this example right quick. Okay. Can you find the magnitude of the torque about the center of the bolt? So the center of the bolt is here. This is the force. This is the angle between them. This is the arm. Okay, can you guys try this for a moment?
Some sine theta.
Yeah. Okay. Okay, let's write down the formula. Okay. What's the formula? Okay, let's write down. See if I remember. So I'm looking for the magnitude of the torque, right? Torque, it looks like a T, but torque, magnitude of the torque. Okay, this is the magnitude of the torque. Okay, and that's equal to what? Everyone? Magnitude of what? R, yes, very good. R, and then what?
Force.
Cos with the force, right? R cos with the force. Okay, very good. Okay, let's get to the next step. How do you find the cos, the magnitude of the cross product? So that will be what? Magnitude of R, right? And then what? Times magnitude of F times what?
Sine
Sine of theta, right? In this case, what is the theta? Yeah, 75 degrees, right? Okay, good. Now let's substitute this in. So what's the magnitude of R? 0.25, which is in meter, right? What's the magnitude of the force? 40 Newton, right? Newton. And then sine of 75 degrees, right? Can you guys punch in the calculator and tell me what you get? Yeah, that's about 9.66 Newton times meter, right? Newton times meter. Okay, so that's the magnitude of the torque. Okay, Newton times meter. Okay. So that's the magnitude. What about direction? Then you use the right hand rule, right? R cos F, right? So R cos F. Okay, so R here, and then F right here. R like this, and then cos F. So R, and R is this way, right? And then F this way, so you cos this. So is it pointing inside the paper, inside that?
Wait,
Right.
show it again.
So here, okay. So if this is this, then the torque is going to be pointed directly down into the page, right? Use the right hand rule. So R here, and then you go to this, then you point directly into the page. Okay, that will be a direction. Okay.